So, in this lecture, we are going to design a column, and our question would be the question is to design a column for a load of 2500 kilonewton. This includes dead load plus live load. The unsupported length of the column is 3.5 meter. So we need to design this column. Now the solution to this is, well, first of all, let's understand the question. There is a column given to us. It is 3.5 meter in length between the supports, and it's not mentioned to us whether the column is a rectangular column or it is a circular column. For the we can first of all design it as a rectangular column, and this is the length 3.5 meter right from this point up till this point. It does not include the support. The support can be anything over this at the top, and there can be another support at the bottom. This does not include this support. Then there is a load on this column, and this load is this is 2500 kilonewton. This is both dead load and the live load that's acting on this column. So what do we do first? We first of all, in the step number 1, we'll be calculating the slenderness ratio of the column. Before calculating the slenderness ratio, we have to fix the dimension then. So what is the dimension of the column that we are taking? And if you go back to 2 lectures, I discuss about the dimension of the column, how you determine the dimension of the column. And we came to know that minimum dimension you should keep for an earthquake design as well. It should be around 300 mm. So for the assumption's sake right now, we are taking, this is an assumption, the D of the column as well as B of the column. We're designing it as a square column, D or B. This is D or B, not to confuse. This is 300 mm. That's the minimum you should take for an earthquake resistant design in zone 5 earthquakes. So the dimension of the column I'm taking as 300 mm. Now this column would have the cross section somewhat like this. This is 300 mm, and you have this as 300 mm. Just a minute, I'm getting a call. So the dimensions of the column are 300 cross 300 mm. Now the slenderness ratio would be, yes, how much? It is the effective length. You always take it as the effective length by d. Slenderness ratio is the effective length by d. In this case, what is the effective length? It's not given to you whether the supports are fixed or not. Now again, we'll assume, because that's a worst condition, when you have fixed supports, then the effective length is the least. So when you have a fixed condition, then your slenderness ratio or lambda equal to uh, how much as per IS 456? Yes, if it's a fixed condition.
So it will be 0.65 times the
Yes,
actual length.
it will be as per, this is as per IS 456. This is 0.65 times L that you have to take when it's, so this is 0.65 into your length, that's the unsupported length, divided by d, which is now 0.3, because I'm converting into meters. Thereby, you have to keep the unit same. So this will be equal to how much? 7.6. Is it 7.6? So this is less than 12. So what is it? Yes,
Sorry, short column.
this is a short column. There are students who are continuously going out and joining again. Then when it's a short column, now your design is, it's not given to you there is any eccentricity of load here. It's mentioned to you that the load is 2500 kilonewton, so it's an actual load. So your load here is actual load and column is short. Now that has to be clear before you proceed on to the design. So then your step number 2 would be, what's your step number 2 now? It is, you have to now determine the eccentricity of the column. And actually you are determining the minimum eccentricity of the column. There is no eccentricity as such acting through load. That's not mentioned in the question. So, but you still have to calculate the minimum eccentricity as per the IS code. And as per IS code, we already know the minimum eccentricity is L by 300.
So L by 500 plus D by 30.
Yes, this one, L by 500 plus D by 30 subject to minimum of 20. Plus D by 30. So how much is this L? What is L? Is it unsupported length or is it the your it's the unsupported length of the column. This L is not effective length. This is the unsupported length. This is 3.5. Uh, it has to be in mm. This has to be in mm. 3500 divided by 500 plus D is your 300 divided by 30. This all is in mm here in this formula. So this is equal to uh, 7 plus 10, 17. 17 mm subject to a minimum of 20. So 17 is less than 20 mm subject to a minimum is of 20. So minimum eccentricity that you would maintain on any such column is being maintained. It is 17 is less than 20. So if there was eccentricity more than 20, then there would be movements as well in this question. So this will not be only an axial load. So now this is clear that it is only an axial load you're taking because it's less than the minimum eccentricity. So is this clear? You, if it's less than 20, then you can assume that it is the only the axial load that's acting. It's only the axial load that's acting here. So step number 3 then is now you actually calculate the load which is acting on the column. You already know the load that's acting on the column here in this question. You have to calculate the ultimate load PU, which is the who is this? So the load acting on the column is ultimate load. Now the ultimate load कितना होगा? It will be 1.5 times the dead load plus live load. So how much is that? Of 2500. How much does this come? कहाँ है सब? Are you solving this?
3750.
3750 kilonewton. So this is the load which is acting on the column. Then once you have calculated the load, which is the ultimate load which is acting on the column, now you know you are designing it as axial load only, and you are designing the column as a short column. Now what dimension you have assumed as of now, 300 by 300, we'll check it out whether that dimension is feasible or not, but we do not need to check it as such. We'll It will come to be known from the, if we go directly onto the longitudinal reinforcement design. So we'll go with the design of longitudinal reinforcement. So how do we design the longitudinal reinforcement? There was a formula For a short axial loaded member in compression, PU is 0.4 FCK AC plus 0.67 FY ASC. So we'll be using this formula in the design. So our PU is 0.4 FCK into AC, then plus 0.67 Fy into ASC. Now we already know PU here, that's 3750. I'll convert it into newtons, 10 raised power 3, that's 1000, is equal to 0.4 FCK. Now, not given in the question, we can assume in for columns, remember this, you usually start from M25 in columns. So let me at this stage assume that FCK is 30 megapascals, that's 30 Newton per mm square. So this is 30. Then AC, we have already assumed that it's a 300 cross 300, but there will be, it will be subtracted as well from ASC. So last time I gave you a formula, this could be converted into AG. Let me convert this first into AG. This is this formula, you are writing it also as PU equal to 0.4 into FCK into AC, not AG, plus ASC 0.67 into FY minus 0.4 into ASC, it's not ASC, FCK. So AG is your 300 क्रॉस 300, जो उसका एरिया है पूरे सेक्शन का, this AG, the whole gross area of the section, 300 क्रॉस 300, then plus you have ASC now, and ASC we do not know, the longitudinal reinforcement dia as of yet, not known. Then this is 0.67 into Fy. Again, we'll be assuming there is nothing given in the question. If nothing is given, then you assume, let's take 500 Newton per mm square. That's Fe 415 grade. Sorry, Fe 500 grade steel you are using. So this is 500 minus 0.4 into FCK is 30. Thereby now you can determine ASC. Yes, determine at your own places the value of ASC.
8266 mm².
8266. What about others? Are they doing it? Yes, someone else? It's 8266.25. 8266.25 mm². Now, if you have a look at this 8266, if I'm using an 32, if I'm providing 32 bar, longitudinal bar, then each bar will have area of each bar is 3.14 divided by 4 cross 32 cross 32, and that is 803.